Welcome to Lecture 11. Today we'll be covering the launch vehicle preliminary design. And in this context, we'll be covering how we develop the loads in a launch vehicle. And I'll show some examples of how you could go about analyzing them. But generally speaking, some of the sizing can be done by hand, and some of the sizing can be done using finite elements. So two approaches, very successful approaches. Um, and with that said, I will start with a lecture showing you the Delta II launch vehicle. And if you go online in YouTube, you will see that a launch vehicle of this kind blew up as it was ascending to space. One of the side rocket motors exploded. But to remind you what a launch vehicle really is comprised of a payload fairing, a spacecraft that's attached to the payload feeding, or payload attached feeding. And this payload attached feeding is then connected to interstage tanks and tanks. Like here in this case, you have a second stage fuel tank and an oxidizer fuel tank, and the second stage RL10 engine. And from there, this interstage adapter is connected to this first stage tank, which comprises of an oxidizer tank. There's space between the first stage tank and the first stage fuel tank. You can see here that they're not sharing a common dome like some of the designs that we saw for the Saturn. And then here you have side rocket motors. In this case, there's over 5 that are attached to the main vehicle, the core vehicle. You have your thermal shield and the first stage engine. So that's your example launch vehicle that we've been talking about. And it turns out that as a launch vehicle ascends, the flight through the varying winds will produce a vibratory bending input. In other words, the aerodynamic loads are going to cause a vehicle to bend, and you're going to have some dynamic amplifications that could occur. As a consequence, it's very important for us to determine which areas we need to beef up to make sure the structure is robust enough to sustain the loading environments is going to see. Because we want to make sure that the vehicle, when it's exposed to the maximum loading environments, which usually could occur near max Q, which is the region of maximum dynamic pressure, that location in time or that point in time, that at every point in a launch vehicle, we have a strong or sufficient strength and is sufficiently sized to be able to survive that ascent. The structure qualification and acceptance test of a launch vehicle heavily relies in the understanding of the aerodynamic environments. If I don't understand the aerodynamic environments, then I cannot go ahead and qualify a structure. It'll be very difficult to do. I first need to make sure I fully understand the maximum loads I will ever see. Typically, in aerospace applications, launch vehicles specifically, we're looking at uh, defining loads that are statistical in nature. I want to make sure it's a maximum load, but I want to make sure it's statistically defined. And typically that is done uh, to define to a level of 9990 as an example. So we have a 99% probability that if you were to look at loads for a particular flight, that those loads will not exceed the loads that you define with a 99% probability at 90% confidence. So not just the strength allowable is defined based on a statistical measure, like A basis or B basis, but the loads you're designing for are also statistically defined. So, for example, excuse me, if I want to look at a diving board, well, a diving board has to survive not just the average weight of the human population. I want to make sure it's designed to sustain it. I don't want to design it to the maximum value. I want to design it to a statistically meaningful value for the weight population. Very similarly for a launch vehicle, I'm looking at the same situation. I'm looking at running Monte Carlo simulation or many different simulations to determine, hey, what is that statistically meaningful 9990 loads that I need to design my structure to. And there's going to vary as you go through the length of the vehicle because the bending loads could impart various loads through it. Here in this picture, you can see the loads they're acting on this launch vehicle. You can see the first mode here and the second mode here as an example. And I'll presume that you have high loads here in this location. Anytime you have high curvature in the deflections, you're going to see high bending moments. So this deflection diagram, if you take the second derivative of this, will show you where the highest bending moments are typically. But those can be calculated directly through a free body diagram and more precisely a couple loads analysis. That will be much more precise. So for me to step into a structural qualification test program, I want to make sure first that I have the loads very well defined. And the structural qualification is important. The structural qualification is the test. It's a test article of the same kind than the one you're going to fly. It's going to be a flight design of the same drawings at what you're going to potentially fly. And so that particular structural design, we want to make sure that particular structural flight design, which has the same manufacturing, has been built with the same processes as the production flight units, that particular design is qualified through a test program. And the adequacy of the structure is defined via this design qualification and hardware acceptance. The design is qualified to account for the part-to-part variability due to assembly procedures, build-to-build variances, and uncertainty in load paths. So we know that every part, when you fabricate it, is going to have a variability. So if I design a part like an interstage, that one interstage may look quite different, not quite different, but it's going to have some variability compared to the next interstage that you fabricate, and so on. Not only because of material variances, but you're going to have tolerances. In addition to that, you're going to have some amount of redundancy in load paths, but you may have some amount of uncertainty in that. Now, that's a qualification test. You take that qualification test article and you test it to failure, and you do that to really understand, I'm sorry, to really understand the limits of the design. So for example, say I have this interstage here, and that interstage has a load from aerodynamic consideration that was found to be 1 million pounds. And 1 million pounds is not out of the question. It can happen. 1 million pounds is the axial load. You could also calculate the bending load across every station along this beam, because a rocket looks like a beam. So you can cut it up and come up with a free body diagram. But at every cut, you can determine the loads for each piece of structure. So taking that load, you will take that load, which is defined 9990, and when you qualify the design, you're going to increase the load from that statistical value to say 1.25 times that load. And the 1.25 represents the factor of safety, which accounts for this part-to-part variability, accounts for these build-to-build variances, and accounts for any uncertainties in load paths. Secondly, the factor could be 1.4. So 1.25 for unmanned, for space vehicles that do not have humans, and 1.4 factor for human space flight. So the flight hardware is typically accepted to screen out poor workmanship or to preclude a hazardous condition such as a leak in a pressure vessel. So in addition to the qualification of a dedicated article, we also would like to look at when I produce. Like now, the qualification test article helps me to ensure that every production article will be successful when it passes the acceptance test. What the acceptance test is another test, but now this test is for every flight unit that you fly. And that test is looking for anything that could be out of the ordinary. For example, you can have a big flaw, so this particular test could screen that out. And so two types of tests. One is a dedicated qual article, qualification test article that you may never fly. Some cases you can fly it, but most of the times you don't. And then another test is strictly done for every flight unit to ensure that you have screened it out for any workmanship issues. The verification requires consideration of all the potential failure modes and all potential load conditions. Potential failure modes that you need to examine in the qualification test program includes all the failure modes we already discussed, like detrimental deformation, material yield, ultimate failure, structural collapse, buckling, fatigue, delamination, failure modes in composites. And loads include quasi-static and dynamic launch environments, acoustic environments, pressure, temperature, gravity, and handling loads. So a large number of test load conditions need to be considered. And of course, you can't test everything to perfection. So you want to come up with enveloping test cases that can be helpful during the test program. And again, you can define the loads through computational fluid dynamics and flight test and wind tunnel test as an example. So here are the phases of flight that we need to be considering. Here are the phases of flight for the SLS launch vehicle. You're going to have launch and liftoff. You're going to have transonic flight. You're going to have maximum dynamic pressure. You're going to have side rocket booster separation. That's going to cause some amount of shock. And the separation event will introduce a flow within the structure that needs to be considered. You then have the launch abort system jettison, and you're going to have then the core reentry, which could allow you to reuse it. And an example of that is a space shuttle. The core, for example, in that case, the tanks were excuse me. So the side rocket motors, I believe, were also recovered. And so that saves you money, and it is a good way of not just saving money, but also understanding system vulnerabilities. Here you can see the space shuttle profile. Well, the space shuttle was retired. I think it's useful to look at the sequence of events. Here you have the liftoff condition, and prior to liftoff, you're really transporting a lot of these parts. You want to make sure that transportation is not inducing any damage to the launch vehicle. And you're going to have some handling damage because you're going to always have tools that are dropping and things like that. So things like that are expected to occur and bound to occur. This launch vehicle ascends now, liftoff, and then you have solid fuel booster separation and the solid fuel booster burnout. And from there you have MECO, which is the main engine cutoff, and then you have the external tank separation. And here you can see that you have these boosters coming off and re-entering Earth. The tank usually will break up, is designed to break up, but these two side rocket boosters are reused. And then you have the shuttle, the orbital system here, that's going to orient it to whatever orbit you want to be. Case number 3 is looking at a different launch vehicle, the same idea. You have liftoff, and here what I like about this slide shows you the times when things occur. And you have liftoff here. You have side rocket motor burnout at 64 seconds. And then from there you have side rocket motor jettison at 89 seconds, meaning the side rocket motor may have burned out at 64 seconds, but it stays attached for another 30 seconds before it gets detached. Then you have main engine cutoff, and that again introduces vibrations to the system. And from there you have second stage ignition, and a second stage ignition that usually occurs about several minutes into flight, very shortly after MECO, or main engine cutoff. That's what that means. MECO means main engine cutoff. And again, this is very useful to understand the system level perspective. And then you have the fairing jettison. So the fairings come apart. We discussed various mechanisms to make that happen. Excuse me. And right after that, not right after that, but several minutes after, you're going to have second stage cutoff. We call that cycle one, and that usually occurs, more than 10 minutes into flight. And then from there, you have another stage, second stage cutoff, and then you have a spacecraft separation, which can happen much later in flight. In this case, the side rocket motors come back and impact the Earth, and they're not useful anymore. And here at the bottom, I'm showing you here in the bottom left. Let me point to it. Here I'm showing you the various processes. I discussed them all as I was walking through, but I'll read it again though. So the first stage, along with the side rocket motors, lift off. The second stage steers the spacecraft into the correct orbit using the onboard guidance system. The fairing protects the spacecraft from heating aerodynamic forces experienced during first stage ascent. So that's over here, all this region here. And then once the second stage out of the atmosphere, you don't need the fairing anymore because in space you don't have any heating environments that are of concern other than the sun, the radiation heating. And you can jettison the fairing. And following separation, the spacecraft, we can deploy the solar arrays because you don't have a problem there. And can orient it to point the array to the sun. And that will then establish the radio contact with the ground stations. Here is case 4, and again, this is a non-human space flight. Here you can see liftoff, side rocket motor jettison, main engine cut off, second stage engine, and then you can see the different kinds of events that I already covered. So there's 2 papers I invite you to download. So pause this YouTube video, download these papers through your library, and or find it through online resources. But these 2 papers really define a lot of the processes that we'll be talking about. The first paper talks about the design and verification of launch and space vehicle structures. And the second paper focuses on the overview of the characterization of the space launch vehicle aerodynamic environments. So the design verification process is highly complex. There's a lot of different organizations that are involved. And I appreciate Oliver Cape for providing some of this material. Dr. Oliver Cape. Numerous organizations are involved, and it can involve the launch vehicle, engines, spacecraft, and payloads. Numerous technical disciplines are involved, like structures, dynamics, fluid, propulsion, controls, flight mechanics, statistics, atmospheric sciences. So a lot of them are really required for us to be able to assess fully the loading environments in an accurate way. The determination of the dynamic loads and stresses involves complex models, usually dynamics, and a fully integrated launch vehicle spacecraft system is needed to be addressed. An integrated system cannot be tested prior to flight typically. That would be very difficult to do. Before flying, I can't really test the full system together. You may have tested the structure structurally, but what about the whole structure as a whole and how the dynamics interact with the whole structure as a whole? You can't really do that before flight. You can do it during a flight test. That can be done, but you're not going to be able to test hundreds of them. You may be able to test 1 or 2. And so you have very limited opportunity to learn about how the flight system works as a whole, which is quite significant here. It's not like an airplane where you can take it for a run every day if you wanted to keep learning about the behavior of the aircraft. There's significant engineering judgment involved. Schedule and cost play a major role in here. the engineering judgment involved here is to ensure that you have all the loading conditions considered and that we fully understand the dynamic environments and we understand all the potential manufacturing errors that are introduced. And you may ask me, well, how is that related to dynamic environments? Well, yes, it is related because if the dynamic environments were significantly high, that could pose a problem for those manufacturing issues you may have encountered. For example, an impact damage event on the composite structure could cause part of the composite structure to debond. And so now you have an initiation point for failure that now needs to be considered in the context of the dynamic loads a launch vehicle may experience. So the loads analysis process, the structural loads are a function of dynamic properties. And these dynamic properties are for the integrated launch and upper stage spacecraft system. And the design changes in one element can result in load changes in all elements. Modeling errors in one element can result in load prediction errors in all elements, meaning this is my launch vehicle here, say. And if I have a modeling error on this particular component, you could potentially basically affect, and I was going to say the word infect, which is probably true, but it can potentially affect the whole dynamics and the dynamic properties of the system. So it's important that every component that we have high confidence for every component relative to um, the testing that may have been done to determine the dynamic characteristics of that component, that our models are consistent to those, because if you were to jump that step and you have an error, then it can affect the dynamics of the whole vehicle. So dynamic properties of each element will be a function of structural design of each element. And so if you have elements that are changing or evolving because the preliminary design was not very strong, then you may want to consider, and you have to consider a iterative design process to be able to make any headways in your design and certification all the way up to launch. So here we have the load cycle process. We have the preliminary design requirements. And in this is straight from a standard. It's called the independent structural loads analysis. And it fully shows the whole process, the whole load cycle process from a dynamicist perspective. And you have here the preliminary design requirements, the preliminary analytical model that's developed, the preliminary design load cycle. So you have your design requirements and analytical model. You want to start looking at some preliminary design load cycles. And then that will help you define some loads that could be useful when you step into your preliminary design review. I went through these milestones before, but I'm giving more granularity as to where we need to spend some time. And it's important to spend time on those loads, because if the loads are conservative, then your final design may be wacky. Maybe it's too thick or too thin. It may not be able to survive the environments that I need for my design. Then we step into the final analytical model. And then here, I'm taking this preliminary design review. I got a lot of feedback from experts. I'll incorporate that and then go into my final analytical model. This final analytical model then feeds into a final design load cycle. This final load design cycle is very important. And a lot of these loads could be potentially enhanced using historical flight data, heritage data, and collaborations with NASA and other organizations can also help inform, how far my loads are from what I expect. And there's also hand calculations I'll be showing you today on some of those loads that need to be projected and predicted. This feeds into a critical design review, and the reason these loads need to be fairly mature is because that's going to now step into my structural models, and I want my structural models and that to produce the correct margins. But I also don't want to have a situation with negative margin. If it's negative margin, I have to go back and redesign, which is totally fine. But that's going to affect now the dynamic properties again. So when you're in that final load cycle, you want to make sure you're as close as possible to where you need to be. And the hope is that when I run my structure analysis, that my structure analysis is fairly robust to the loading environments I came up with. It is important now that if you pass the critical design review, you're able to release drawings. And if I release these drawings, what I want to do is check. I don't want to have a situation where the manufacturing process came out not correct, and that could be a problem by itself. So after here, every component now is compared against, or it's checked against model survey. And what model survey is doing is you're hammering the component, you're getting the vibration frequency, but also the mode shape. And so what this is doing then, this mode survey is verifying that the dynamic properties that you have used in this vehicle is correct. For example, I went to Yellowstone as an example, and if this coma, if this if so, are you guys following me? Hello.
Hi, Professor. I don't know about anyone else, but I wasn't able to hear the last 15 seconds.
Okay, I am having difficulty with this lecture because I'm getting the same issue I've been getting the whole quarter semester, which I'm not getting with at work. So can I complete this lecture, this particular page, and then perhaps come back? Hello? So can
Yeah,
you
that
guys hear
sounds
me?
good. Yeah.
So what I'm thinking is I'll finish this slide and then I'll basically finish recording tonight and post it. Is that okay?
Yes.
Yes, that's fine.
Because clearly there's a problem and it's causing trouble. So the mode survey test becomes very important to verify the models, and then you verify the models and you go into a verification load cycle. In the verification load cycle, we're looking at performing an independent verification validation, and we want to make sure that the models are correct because these models are highly complex. There could be a lot of errors. Both on the spacecraft and launch vehicle side, there could be errors. And so it's quite important to make sure that we have fully vetted these models and any corrections are made. If there is big errors, it could affect um, the design, and you may have to go back and even potentially have to fix the design, which means you may have to go back and either make the structure more robust and figure stuff out because it would be a very painful situation if your lows are too high compared to what you initially assumed. So you want to resolve the differences between the organizations to make sure that the laws are being used and the design are correct. If the laws are correct and everything looks great, you can step into the final assessment of the structure qualification. And if the structure qualification passes with the laws that you came up with, they're fully encompassing, they have gone through a lot of vetting, then you can go straight through flight. But if there are issues, you may have to consider limiting the day of launch allowable, meaning I may have to, instead of flying in a day that's very windy, I may have to wait for the winds to die off so that the loads on the vehicle are less. Because I'm not too confident about these loads, I may have to put placards in my design. Meaning placards here means I'm limiting the design space when it comes to launching my vehicle because the loads could be too high. So I'm going to select maybe a different day where winds are a little bit more benign. So I want to continue discussing the launch availability. Um, and to achieve the required launch reliability, many launch vehicles have to be placarded. The placards can be the placards can be divided into two families. One is a launch placard, and the other one is a flight pack placard. The launch placard typically will include ground winds, for example, and lightning, cloud cover, temperature, or something else. Atmospheric flight pack placard, however, include flight loads, trajectory, control performances, and things like that. If the launch vehicle and the payload are sufficiently robust, you can demonstrate that the reliability requirements for launch and flight loads, vehicle control, and performance can be can be really met without day of launch placard calculations. But you still have other constraints such as cloud cover, lightning, toxic constraints, and other things like that that could push the launch availability to be less than 100%. For launch vehicles that require placarding for loads to meet reliability requirements, the only way to increase the launch availability is to either increase the structural robustness or you decrease the launch reliability. You have only two options. And it hasn't always been assumed that all the conservatism has been removed from the liftoff and atmospheric flight loads, and that there's not a lot more you can do. Um, and so there's always going to be pressure to try to launch that same day if you can at that particular time. I also want to make the point that because of the significant flight to flight variability you can have in the forces that act on a launch vehicle, all loads analyses have to be performed, like I said before, they have to be performed to a load level that has been statistically defined. And those values should not exceed a particular value, and that value is established for based on the customer's requirement. For allowed space systems, the loads analysis are typically performed to obtain no less than 99% enclosure with a 90% confidence. I discussed that earlier, but there are cases where people have gone to 99.7% enclosure level with 90% confidence. So while there's not a lot of, there's no commercial standard that prescribes a number, there have been loads calculated as low as 95% enclosure with 50% confidence. And the other thing is, if you have a loads problems late in the game, say past CDR, and it could be tempting to reduce the calculated loads by simply redefining a new statistical value. And again, you're sacrificing now the potential of decreasing reliability because of doing that. So you have to be very cognizant that reducing that statistical um, high bar can now you're trading reliability by doing so. And so it is of great importance that we do pay attention to that, and that we are cognizant that the analysis that is performed has to be robust enough so that we don't have any issues during flight. There's also an important aspect of this where we have to discuss the various organizations. So when I'm talking about IVMV and I'm talking about this column and this column of boxes, what I'm really talking about is ensuring that the spacecraft and launch vehicle, these two things together can operate correctly and really well. Because there is this potential that the spacecraft could exhibit loads that are quite significant to the point you could break the spacecraft due to the launch vehicle vibrations. And so it's important to develop those forcing functions with high confidence because those forcing functions could drive a spacecraft to failure, or your analysis is incorrect, so it could overestimate the structural margins of the spacecraft incorrectly. Another thing I want to point out is that there are also issues with spacecraft not providing a full model to launch vehicles. Notice that the launch vehicles and spacecraft are different organizations. And so there could be a disconnect between the two models, and they're really trying to develop these things on their own. But when you combine the two late in the game, that could cause a problem on the spacecraft side or the launch vehicle side. I apologize. And so again, it is, the structural design process is typically initiated early in the game. I want to go back early in the game. Is really initiated with a set of preliminary acceleration design load factors. And a lot of launch vehicle users guide, which I've shown in this class, provides preliminary design load factors, but they're usually not enough to ensure the adequacy of the space vehicle structural design. And so proper set of design load factors needs to be accounted for to, to really address the unique features of that spacecraft. Again, since the launch vehicle site does not have the visibility of space vehicle programs, then that could be a problem. Once you have a preliminary design early in the program, you could start developing some analytical models. And these models will usually be reduced in size and is going to give you some amount of information that can help you start developing a better understanding of, with the forcing functions, a better understanding of how the spacecraft will perform when it's attached to that launch vehicle. You don't want that spacecraft to break off due to launch vehicle vibration. So that becomes very important. And so it is important that the models be validated, um, because if those models are not validated, then you don't have high confidence in 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 the margins that are predicted for that spacecraft. And it is very rare to obtain analytical models that do not require adjustments. You usually have to adjust the models to match mode survey data. And so therefore, mode survey is again, mode survey is a way of calculating the dynamic properties of the components. And you need to make sure that the launch vehicle model and spacecraft models are adequately anchored dynamically. Otherwise, you're going to have error in the predictions. Also, usually models do really well with the first two global bending modes. The fundamental axial mode tends to be less certain, and the fundamental torsion mode is usually even less certain because of the complexities of modeling torsion. You also have spacecraft components like appendages. Say you have an attachment like an antenna. Those tend to be uh, modeled, but tend to not correlate very well with test data. And so, again, it's very important to consider these points because that drives the loads that you need to then test later. And if those loads are incorrect, then you're going to have a significant issue with the design. And so, I do want to cover then the idea of the couple loads analysis. The couple loads analysis usually takes a spacecraft and attaches that to the launch vehicle. And people usually use a Hurdy-Craig-Bampton model to do that. I'm not asking you to become an expert on that right now, but I'm just simply letting you know that that is something that is done. And there are situations where um, these models are complex, first of all, and you need to make sure that these models are accurate. Otherwise, the prediction for loads will be incorrect, which will be very difficult to really um, fix late in the game. And if there's a problem late in the game, then that can be a problem in those qualification tests you may have done may be invalidated. I also then want to point out that the loads analysis model involves a lot of different technical disciplines. You have the idea that spacecraft models have to be attached to a launch vehicle model. And here I show you different colors that corresponds to the various areas of expertise. You can see here structures in blue. You can see in gray is a structural dynamics, and in green you have guidance and analysis. This is dark green. Light green is fluid mechanics, and then you have the flight software. All these areas of expertise have to work together. First, here in blue, you see the drawings, the static mode survey, and other tests, and flight data. All that goes into the finite element model. You have to, once you develop the finite element model based on drawings and information about the part, you want to then check it against mode survey and other tests, static tests, and things like that to make sure it's an accurate representation. The flight data can also help improve the finite element model only if you have some initial flight test data. Um, and for component number 2, so 4 up to component number n. So that will be true. And then from here, you go and develop your dynamic model. And again, mass properties plays a big role to make sure, because dynamics depends highly on the stiffness and distribution across a component, but also it is going to depend highly on the mass properties and making sure those mass properties are correct. When I say LTM, I mean the load transformation matrix is important. I won't go into the details of that. The bottom line is that you want to make sure that the finite element model for dynamics is properly developed. Usually you're going to have two different models. One is a coarse model for dynamics, and another one is more for stress model. So a coarse model for dynamics, a refined model for a stress analysis. That will give you a lot more detail and is going to tell you where structures could fail. While the dynamic model is really intended to understand the loads in the part. And so all that goes into the loads model that's attached to the spacecraft model. And this spacecraft model is developed in unison between structures and structural dynamics. And another important part here is guidance and control. The guidance and control is going to tell you the trajectories that it's going to take. And so here's where guidance comes into play, and that defines the autopilot and engine actuator definitions. That goes in here. Then you have also the fluid mechanics side of things and flight software. This is going to give you information about the hydroelastic model of the fluids. We'll be talking a little bit about that, but not too much later on. Fluid mechanics does significant amount of work using wind tunnel testing, computational fluid dynamics, and that actually provides quite a bit of the forcing functions that goes into this loads model. All of this together provides you the loads, is going to define the loads required that are going to help you then assess the structural system or design the structural system. And in either case, you can see that this could be an iterative process. It can involve several months of going back and forth until you have reached some sort of equilibrium. Accurate loads analysis models can only be achieved with test verification. Okay. And so substructure models can be easily over 1 million degrees of freedom, and 5 to 10 million degrees of freedom is not unusual, and you can see that. Detail required to model complex hardware makes this computationally very costly and can take months of effort to make sure you have the right models. A lot of engineering judgment is involved because you can't model every nut and bolt, but you also cannot ignore major details. So you have to really balance to make sure these dynamic models are sufficient. There's not overkill, but it's also not ignoring too many details of importance. So static and other tests are performed to qualify the structure to analytically predict loads, but you do have to also adjust the structural models to make sure they're highly accurate. So these dynamic models can also be adjusted based on testing that you have done statically, because you may find things are incorrect in this model. And that points to the fact that there's an iterative process here that involves both static testing and mode survey testing. Mode survey testing basically take a hammer, hit the structure, make sure that the modes that are seen in that structure are representative of what the model shows. So there are several load environments of high importance. We have the liftoff events which can, that's basically liftoff. And liftoff includes ground winds, which I'll be talking a little bit later, thrust transients, gravity, atmospheric flight, static air elastic loads, gust, which really involves rapid changes in wind, buffet loads due to local turbulence and shock, engine ignition and shutdowns, staging and separation events, transportation environment. So all these load events have to be considered in the design. You have to come up with an envelope of these loads so you can drive the design and ensure that that structure is statically strong for the loads you're going to see in flight or transportation. Here is an example of a computational fluid dynamics model simulating the engine plume as well as a free stream air for various combinations of engine gimbal angle and vehicle angle of attack and velocity. You could have pressure loads that could be quite significant that could drive some of these load events. Again, the load events can be calculated per station. You can have a different load event in this area compared to the interstage or stage tanks and things like that. Again, I'm highlighting two important papers that can be of great value as you study this. Let me hit a liftoff here for a second so we can go a little bit deeper about what is going on there. So liftoff is a nonlinear transient phenomena, and it includes a vehicle launch stand interaction. So here you have your stand, and then you have your vehicle, and there'll be some amount of interaction between the two. It produces critical loads for launch vehicle and the spacecraft structure, and the forcing functions are going to include the thrust transients and differentials, ignition over pressure pulse, and ground winds, gravity. Gravity is a major component there. Launch stand interaction, which I just talked about, and dispersions. Modeling consideration is that you want your a model that can get up to 60 hertz of data for your modeling, and the finite element of the substructures have to be transformed into component mode models. You also want to have hydroelastic models of the fluid because everything is full of fluids like stage tanks and things like that. And you also need a coupled system damping as you go through this analysis. More importantly, the liftoff event, I think it's very important to point, is a nonlinear short duration transient event, and that the forces acting on the vehicle can be quite significant. Ground winds particularly can be quite important. So it is not unusual for this event to be the primary design condition for the aft end of the vehicle, the launch vehicle and space vehicle interface area, and other areas of the vehicle as well. The liftoff analysis typically requires a nonlinear simulation to properly define the launch pad launch vehicle interface, and the response of the system can either be derived in a nonlinear simulation, and it can also look at interface forces from this simulation, which could drive additional analysis. So, because of the need to define launchpad interface forces, the displacements at this interface need to be defined. You have to get that right, and those flexibilities need to be correct. Otherwise, there could be a problem. Other things I want to point out, there are stresses due to direct acoustic impingement, and that needs to be looked at. You also have the issue of acoustic excitation, and it is important to understand that the space vehicle acoustics test does not induce the total load that the primary and secondary structures will see. Okay, and so these loads, you can apply them in a static strength test. That could be one way. The static test load should be the combined low frequency transient values obtained in the liftoff simulation. So you're actually analyzing time, events, and so liftoff is one of the events you want to look at. Um, and also, I want to point out that the maximum acoustic environment that is used in acoustic test does not necessarily coincide in time with the maximum transient liftoff loads. It could be a different point in time. And so therefore, the acoustic levels are proper for the liftoff transient event should be used in analysis. Again, acoustic tests should be performed to verify the accuracy of the prediction process. So that's one thing to really consider as we talk about liftoff here. I will be talking about ground winds a bit later, so you have it very clear on what's going on there. I want to cover a little bit deeper what's going on with the ground winds and liftoff aerodynamics. It is important to understand what is going on in this phase. So there is low speed aerodynamic environments, and it moves in a direction that is mostly perpendicular to the launch vehicle axis and is modeled by measurements of the typical wind profiles experienced at the launch pad. We'll be talking about that a little bit later. Similar to the ground wind environments, because this is the ground wind environments I'm talking about, the initial liftoff aerodynamic environment encountered by the launch vehicle behaves a lot more like a ground wind. But as the velocity of the vehicle increases, it will transition then to aerodynamic environment. And in this case, the free stream airflow is mostly parallel to the launch vehicle axis. But you can see how, as the vehicle is stationary, the ground winds that are perpendicular to the launch vehicle axis start to transition to more of an aerodynamic loading environment. These ground wind and liftoff aerodynamic environments need to be assessed during rollout and at the pad. And also at the vehicle, you have to also look at vehicle trajectory, added to control during liftoff, and that's at the initial seconds of flight. You know, you can use computational fluid dynamics and analytical methods based on historical data and wind tunnel testing to support the design and analysis. The CFD analysis is typically anchored for all ground winds and liftoff aerodynamic databases. You will have CFD analyses that's looking into this very carefully and making sure your models are anchored very well. Here's an example of a wind tunnel test, and here you can see a mock-up of a launch vehicle. This launch vehicle is going to be subjected to ground winds and liftoff aerodynamic testing to fully characterize the loading that the vehicle is going to experience. And so you can use scale up factors to come up with the loads it's going to experience when you go full scale. But if you create a CFD model of this vehicle and with a wind tunnel test, you can anchor that model to this scale model and demonstrate that that model is adequate, and then use it and then go to a CFD model of a larger scale to try to see if everything is making sense. Um, there's also the issue of liftoff ignition overpressure pulse, and that could be a significant amount of load that's imparted on various parts of the vehicle. A computational fluid dynamics model can be quite expensive. It can, 3.5 seconds of real time can mean a lot of computational time of analysis, even using 30.7 million cells, 120,000 CPU hours, or even 5,000 CPU days. It's a very, very expensive model, even for short duration, because to model the liftoff ignition overpressure pulse is not very simple. I want to go a little bit back and discuss a little bit more about this wind tunnel testing. So, in essence, you will get a flow visualization technique, and you can look at how the flow is moving through this part. The testing can help you determine the vehicle bending moment, and it can provide you the integrated forces across the vehicle. And it's going to give you static pressure measurements also, which are distributed spatially on the vehicle and can help you then compare to CFD. And it's going to help you with the determination of the aerodynamic loading on the external components of that vehicle. So very important testing that is performed that provides significant amount of value on this kind of analysis. And again, wind tunnel testing plays a big role in what needs to be done. Here's an important paper by Majamaki on the CFD simulations of launch environments for Delta vehicles at the Slick 6 launch pad. It's a great paper that goes into those kinds of simulations so you have a better understanding of what may happen in those simulations. And so I'll touch a few points about this paper. So as the engine starts up during liftoff of a launch vehicle, you're going to have nozzle exhaust gas fluctuations, produce ignition overpressure, it's called. This ignition overpressure is a key component of the liftoff loads on the launch vehicle. Typically, the launch vehicle is mounted on the launch table, and then you're going to have these exhaust gases coming from the launch vehicle engine, which will travel down the table and through the flame duct before exiting the flame duct at a significant distance away. These ignition overpressure waves that rise up from the launch table and travel up the vehicle, we're really talking about and they're referred as the inlet ignition overpressure waves. The ignition overpressure waves that exit the flame duct and travel back towards the vehicle are referred as the exit ignition overpressure waves. So the magnitude and directions of the resulting ignition overpressure on the vehicle are highly dependent on the combination of vehicle and launch pad configuration. So here you can see the flame duct here, and you can see those are the exit waves, and here are the the inlet waves. So they're traveling up the vehicle from the launch table. And you can see how all these can be an important consideration to take into account to really predict those really well. There are 1D models that have been used in the past, but 3D models are preferred. They provide quite a bit of information about what is going on with these pressure events that could be of great importance. And again, like I said before, it can take significant amount of time to run a model like this, and it is going to be computationally very expensive. So it's important when this analysis is performed, it be you want to make sure it's as accurate as possible from the get go. Another thing I want to point out is that you begin the simulation a little bit early, t minus 3 seconds, say, and at this time you're going to have the engine chamber pressure slowly increasing, and that usually occurs, and then you go into a little bit later, but t minus 2.5 seconds, say, and during this period the chamber pressure rises usually very, very rapidly, and the nozzle becomes fully choked. But the chamber pressure is usually just enough to choke the throat, so you get a strong normal shock that forms at the beginning of the diverging nozzle. When a shock is formed, the first significant pressure wave will propagate out of the nozzle and then up the vehicle as well as down through a launch duct. So that's very important to really consider. And as you move on, you're going to see, let's say t minus 1.5 seconds, the plume will become fully expanded, and it's going to travel along the vehicle. And all these things need to be considered to get a a good handle of the launch vehicle loads. I want to talk a little bit now about atmospheric flight loads. Let me discuss atmospheric flight loads a little bit. And this design condition does occur for the majority of the portion of the launch vehicle. Atmospheric flight loads are predicted by combining the results of separate analyses. The analyses in this case are performed at discrete times in flight with models that represent the coupled system at the analysis time of flight, because the vehicle is changing due to the mass that's been expended. And you could have parameters that vary, which could include the mass properties of the launch vehicle, the tank pressure, and vehicle configuration. As a minimum, the transonic and maximum dynamic pressure times of flight need to be considered. It is not unusual to interpolate launch vehicle loads from, say, two sequential time points in flight, because you want to then obtain intermediate points in flight. You have to be careful how you do that. The most important contributors to atmospheric flight is really the static aeroelastic loading, loading due to atmospheric gusts, buffet loads, control system induced loads, thrust loads, and drag loads. And I'm showing them here right now. You have the static aeroelastic load, and in this case, it's due to relative wind and non-zero angle of attack. So you have the angle of attack the relative wind relative to the vehicle axis, and that could vary slowly relative to the fundamental mode frequency of the system. Then you have the turbulence gust, which is a non-persistent wind that say it looks like this, that causes changes in the local angle of attack. Then you have the buffet loads. The buffet loads is an interaction between the separated flow turbulence, here as an example, attached boundary layer turbulence and shock wave oscillations. Then you have the autopilot induced oscillations, or sorry, loads, which is maneuvering and steering. So these are maneuvering force and thrust load, and autopilot noise, and mechanical noise from, say, as an example, engine gimbal friction. Other analyses could include lack of wind persistence and dispersion. So atmospheric flight loads, you can see here, it includes a number of them. A number of those loads have to be looked at. And so let's look at some of these components. Here you have the unsteady aerodynamic environment acting on the launch vehicle. So as an example, aerodynamic buffet loads manifests itself as a lower frequency cyclic fluctuating pressure over an area of the OML. You can, characterization of these environments is highly important because as this pressure fluctuation can manifest itself as a periodic force acting on the vehicle, that can actually cause catastrophic results during flight if we're not looking at that carefully and is coupled with the vehicle bending mode. You could also have higher frequency random noise, and it may not be on the entire vehicle, but you're going to have them. Flight aeroacoustic environments can drive the design locally, and it could maybe even make you think about maybe putting the avionics system at different locations to avoid any interaction between this high frequency noise and the avionics. And aeroacoustic loading testing can be performed in transonic wind tunnel testing. Very important to understand that you can look at that in the wind tunnel testing, understand those environments a little bit better. Atmospheric flight loads, they're computed at various times, like I said, 10 to 20 Mach numbers typically. Transonic and maximum dynamic pressure times of flight tend to be the most critical. You have to look at this. Transonic maximum buffet load will yield design loads for significant portion of spacecraft. Maximum dynamic pressure will yield critical launch vehicle loads and some significant spacecraft primary structural loads. Very important here, maximum dynamic loads is going to drive a lot of it. And this can occur when the flight is going through a jet stream and you may have like even high turbulence gust loading from turbulence. And the loads analysis has to incorporate the structural dynamic models, aeroelastic effects, control system atmosphere, and thrust effects. Then you have the buffet loading conditions. But I do want to point out that the static or elastic load, which I discussed earlier, you do need to include rigid body translational acceleration effects, and you also want to look at you want to calculate these loads, and they're only calculated at the day of launch. Wind velocity as a function of altitude, because the wind velocity as a function of altitude is measured prior to launch by tracking balloons. So you use balloons really to inform the wind velocity. That's why those become important the day of launch. And then you can come up with a steering parameter, which will then minimize the angle of attack relative to the measured wind profile, because you don't want to have a huge angle of attack. I'll show you later. If you have a large angle of attack, that's going to influence the amount of bending loads you introduce into the vehicle. So the steering coefficients are then used in a flight mechanics simulation, and an altitude history of the vehicle's pitch and yaw angles of attack are calculated. Those altitude histories are then used to derive these aeroelastic loads we're talking about as a function of altitude. So yeah, I want to bring that up here because it's relevant to what I'm discussing here. Buffet loads is quite important as well, but I want to go back a little bit to I'm sorry, I want to talk about the buffet loads. Yeah, the buffet loads are relatively long in duration compared to other transient events, and they're treated as a steady state random process. The objective of this analysis is really to compute the probability density function of response quantities such as loads from a statistical enclosure value using either the mean and standard deviation and a Monte Carlo analysis. So in reality, the Buffett analysis is really performed to establish the loads due to this dynamic response of the vehicle payload system to shock waves, flow separation due to changes in vehicle geometry, and the interaction between the two. So for most vehicles, the analysis is performed in a frequency domain, and the forcing frequencies are described in power spectral densities. There has been time domain approaches used in the past, and which could use relatively long time histories, and these can be obtained from wind tunnel testing, like I just discussed a little bit earlier. And you can then integrate these equations of motions numerically, and then calculate the response of the structure. In addition to the atmospheric flight loads, other analysis can be performed looking at this Buffett loading carefully. And then you have this, here's an example of aerodynamic environments in a wind tunnel test. And on the left-hand side, can see the Langley Research unitary planned wind tunnel test, looking at the aerodynamic environments. On the right-hand side, you can see the Boeing Polysonic wind tunnel test. And this medium fidelity force and moment aerodynamic testing can really provide a lot of information on the vehicle dynamics and the loading environments that you may see. And so, yeah, so that's quite important. I want to point out that the aerodynamic induced forces and moments in this kind of tests are one of the first aerodynamic products that engineers really use to predict the vehicle control, trajectories, payload performance, and so forth. And that's why it's so important to get this data right and provide, and you can use previous database to really inform that. And the use of CFD has really an important role in launch vehicle development, and it's an integral part of coming up with these load environments. But wind tunnel testing really provides a cost-effective approach to accumulating the large amount of data that's really required to understand the force and moment databases are used for the design. And also, when you compare this testing, it can then increase the confidence in the CFD analysis for looking at aerodynamics at various times of flight. Looking forward here, then, we have the aerodynamic environments from booster separation aerodynamics. Here, what we're seeing here is a side rocket booster separating from the SLS in this case, and this is going to provide some amount of loading conditions into the vehicle due to this separation event. And in a space shuttle, for example, which you could look at, for example, the side rocket motor had to be safely separated from the core during vehicle ascent. And anytime you have a separation event, you're going to have a predominant force that affects the motion of the launch vehicle component, and it can be quite important to consider. This separation system will produce a complex flow interaction between the free stream flow, and the supersonic exhaust plumes from the rocket. And so, in such a complex scenario, CFD is typically used, and you want to then figure out a way of determining whether these analyses are valid. You can also look at, you definitely have to rely on CFD on this one, and maybe very limited anchor test data may be available. A wind tunnel test to cover all the potential ways to look at this could be quite expensive, and so that's why this kind of simulations are done with computational fluid dynamics. I want to touch upon gust loads. Gust loads are going to are performed to establish the dynamic response of the launch vehicle and the payload due to turbulence, and that might be encountered during atmospheric flight. Typically, you're going to have these are short duration typically, and these analyses are typically performed with models that have a frequency content up to 20 hertz. Most of the primary response is below 10 hertz, so that's okay. And the amplitude, wavelength, and shape of the gust are selected such as the induced load in the coupled system are equivalent to the desired level of statistical conservatism we talked about earlier. And to establish the proper loads, the simulation has to include the elastic stiffness, damping effects, and also the vehicle control system induced engine side forces. The control system is required to obtain proper rigid body response of the vehicle, and you definitely want to get this right. Again, these are relatively small scale, short duration wind features, and the loads analysis performed are fully integrated structural dynamic or elastic control system simulation. You look at synthetic profiles, turbulence profiles extracted from measured winds, so Monte Carlo, and you can see here an example of this behavior of the turbulent gust. And you can see here um, the calculation of the various factors. You have the wind speed here and the turbulent gust added together to give you a more complete panorama um, picture of what is going on with the total load response. We also have to look at wind persistence and gust loads analysis. You have rapidly and slowly varying wind components, which can be separated. So rapidly and slowly varying can be separated. The boundary is a function of how far into the future one wishes to predict. So here's an example at 60 minutes. And then here's example 45 minutes. You can see that the differences from going to 60 to 45 to 30 minutes, the wind magnitudes. And here on the y-axis, I have the average wavelength. On the x-axis, the lack of wind persistence time, and a plot here where at the top you have the slow varying region and the turbulent region. So the wind persistence does play a big role in the gust loads analysis. Here you can see that, and I'm sorry for this font issue, but you 60 minutes before launch, you can see how the magnitudes are more severe. But as I start to look at less time before launch, things get more straightforward. And here's a paper I recommend you read: a refined and less conservative day of launch atmospheric flight loads analyses, so you can get a better understanding of that. Increasing this way is increasing the turbulent component. So 60 minutes before flight, you're increasing that uh, turbulent component. If you go and look at less time before launch, you're looking at increased persistent components, both playing a big role in the day of launch placards that I talked about earlier. Here, the atmospheric flight loads then has to consider total combination, and here's the equations that people use: statistical combination of time varying loads, and you're looking at turbulence, gust, thrust oscillations, and buffet, and all three had to be combined to give you a total effect and be able to give you a good understanding of the loads on acting on the vehicle. Here, what I'm showing is the launch vehicle phases of flight. Here I have the on pad. So for on pad, I'm looking at ground winds, launch stand interaction, and gravity. Some amount of buffet loads and tank pressurization. Then at liftoff, you still have some ground winds, some launch stand interaction, thrust transients and differentials, and then gravity plays a role in gust loads, buffet loads, and maneuvering and tank pressurization. And then you have transonic flight, and you can look at this table carefully, and then payload separation and so forth. Here, what I'm showing is the various phases of flight and the source and the method of estimation. For example, ground winds, the method of estimation for that is environmental analysis, CFD, wind tunnel testing, statistical analysis, and so forth. Launch time interaction can involve finite elements and CFD. Thrust transients is going to include some proportion with CFD. Ignition overpressure, again, CFD is going to be playing a role in that and the propulsion system. Gravity, the source is Earth. The couple of those analyses, environmental analysis, and finite elements can be of help there. And then again, the statistical aeroelastic analysis is going to include CLA, aerodynamic analysis, CFD, wind tunnel testing, and so forth. So this just gives you kind of a big picture of what ways you have to estimate these loads. Maneuvering and steering is going to involve the GNC team, and the source is autopilot noise, mechanical noise. Sorry about that. You have the tank pressure, and that's going to be the source where there is a ullage pressure in tanks. And again, the proportion system analysis will give you a lot of that. Separation loads, we talked about how CFD can be of great help here. And um, and so once you go through these analyses that provides you the loads across a whole launch vehicle and at different times in flight, you can then use that information. So the first step is to develop a finite element model of each of the launch vehicle components. The launch vehicle component typically is going to be a fairly coarse model, and the coarse models are going to be then attached together into a big model. This model is a couple of analyses, and in this model, you're going to calculate the frequencies and mode shapes up to 70 hertz. The finite element model has to include nodes at load recovery points. So a critical interface, let's say I want a critical interface at this interstage. So if I have this interstage, I want to have a recovery point here, every so often, because that's going to give me the information I need to then run a test, for example. So the finite elements are then integrated into couple loss analyses, which is a system level dynamic analysis. Again, two types of models. One model is intended for a dynamic model. Another model is intended for stress analysis. So you'll take the drawing, right? Take the mesh it, so use finite elements, and then integrate into a couple of those analyses, which will have all these components, integrate into one system, including the spacecraft. And so that model is going to give you important information, driving load events for each of the things we talked about, like liftoff, atmospheric flight, engine ignition and shutdowns, staging and separation events, and so forth. I did want to talk a little bit in engine ignition and shutdowns because I failed to talk about it earlier. But they do produce critical loads in the vehicle. And the severity of the events really depends on engine parameters, such as the design of the injectors, the length of the fuel, oxidizer, types of propellants you use, mixture ratios, and timing delays in the engine igniter electronics, and so forth. Extensive flight data could indicate that you're going to have variability from flight to flight, even for the same vehicle, because every engine performs differently. And so it is important to consider engine ignition and shutdowns statistically. The preferred analysis for engine ignition and shutdowns is to use thrust forcing functions derived from engine thrust chamber pressure measurements. And you definitely want to use actual flights if you can. If those are not available, then you can use ground firing test data to kind of anchor it. And that's less preferred. Um, and so, you know, another way is to use synthetic forcing functions. And those can be derived using analytical engine simulations, knowing the knowledge of the engine parameters and how much you're allowing dispersions there. So yeah, I want to point that out because I forgot to cover that aspect. But engine ignitions and shutdowns can play a big role in the staging and separation events as well. So when you run this couple of loads analysis, which is a dynamic analysis, um, that dynamic analysis will then produce at different stations an axial, shear, and bending moment. For example, here is the compression axial load predicted by the dynamic analysis, and you will have the bending loads and the axial load at different stations, and that information is used to then inform the structural testing or analysis that needs to be performed. And I'll cover what to do with this later in a future presentation. But for now, I do want to cover how will you go about, say I don't have this luxury of performing this highly complex dynamic analysis, which is the way to do things. But I do want to produce or explain top level view. What are the ingredients of performing a preliminary design of launch vehicles on a piece of paper? So you want to treat, and I will go through this so you can see the key ingredients, but it doesn't mean that it's going to give you all the information you need to perform a super accurate analysis when it comes to the preliminary design of launch vehicles. The approach I'm going to use to solve this problem is to treat the launch vehicle as a rigid body. And we'll just use basic free body diagram, and we're going to determine the shear, axial load, and bending moment across the whole vehicle. And that information will then be sufficient to then step into a structural assessment. I want to make sure you understand that this is just for preliminary design. It's not intended to be your final answer. You want to use a more comprehensive dynamic analysis. In this case, we're treating everything statically. The data you require is the angle of attack and all this information I talked about. Aerodynamic coefficients can be found through wind tunnel testing. And then you can also use empirical data or closed form solutions for cone cylinder geometries to come up with these aerodynamic coefficients. So again, angle of attack as a function of time, dynamic pressure as a function of time. Those are key ingredients in this analysis, including the Mach number. So I want to show you the process on how to do this. Here, you're going to put the weight at this centroid of each of the components. So W1, W2, W3, and W4 as an example, and W5 for this nozzle. And the diameter here is D1, D2, and here I have the relative distances, X5, X4, X3, X2, and X1, and that's going to be useful when I do the calculations. Sorry about that. And so the weight and CG location for each component relative to the CG of the vehicle is known. So let's say this is the CG, the red dot. And the end goal is to determine the shear bending moment diagram given the Mach number, angle of attack, dynamic pressure, and geometry of the vehicle. Mass properties can also play a role. So for hand calculations, it is a reasonable assumption that the lift and drag is really solely created by the cone and truncated cone sections. So only this section and this section are the only ones that will cause the lift and drag when this vehicle is at an angle of attack relative to the free stream. And the coefficients of lift and drag can be determined from CFD, which is correlated to wind tunnel testing as a function of vehicle length. So here, CL and CD, again, they come from aerodynamic testing or wind tunnel testing. The lift and drag forces will be the highest at the cone cylinder. So you're going to have the cone cylinder and the truncated cone cylinder. And they'll be determined based on the lift coefficient and the drag coefficient, the dynamic pressure, and the projected area AI. So in this case, for this cone here, you get a lift. So say this is an angle of attack. The angle of attack causes a lift which is perpendicular to the direction of motion, and that's why that's perpendicular there. And that's your load, that's lift. And that lift is calculated as the dynamic pressure Q times the projected area AI. And then you have times CL, which is a lift coefficient. Then you're going to have drag, which is acting perpendicular to the direction of motion. So since it's moving in this direction, you're going to have drag in the opposite direction. And that's true for this component and this conical component. Here, what I've shown is XP1 and XP2, the location of these loads relative to the centroid. W is the weight of the vehicle, T is the thrust, and I'm putting the full weight of the vehicle at the centroid. The drag coefficient is typical 0.7, typical value, but it could be higher or lower. The lift coefficient can be determined again from wind tunnel testing or empirical data, and it is dependent on the Mach number. Very important to consider. Now, the incident area or the projected area can be calculated for cone 1 as if the diameter is d1, sorry about that, then you have pi d1 squared divided by 4. And the projected area for this truncated cone is a ring. So if the outer diameter is d2 and the inner one is d1, then the projected area is a ring, which is pi d squared minus d1 squared divided by 4. So again, you only have two of these here. Then I can take this lift and drag and decompose it. I can put it into the horizontal and vertical axis. Each of these components can be decomposed. So I've done that here. So I've taken, for example, S1. The contribution of S1 comes from L1 and D1. So I have to decompose D1 into this direction and the vertical direction, L1 into the horizontal and vertical direction. And when I do that, I get the L1 cosine alpha plus D1 sine alpha for S1. And S2, for the one here, you get L2 cosine alpha plus D2 sine alpha. You can see that here, L1 cosine alpha goes that way and D1 sine alpha goes to the right. So adds up. And the same thing for this one here. Now, when I look at the force F1, which is vertical, the contribution there is that L1 now is in this direction, upwards, L1 sine alpha, while D1 becomes D1 cosine alpha pointing downwards. So F1 is minus L1 sine alpha plus D1 cosine alpha, and F2, I can do the same calculation here. F2 will be the minus L2 sine alpha plus D2 cosine alpha, where L and D are the lift. L2 and D2 is the lift and drag loads. So therefore, the gimbal force, because you're going to have a gimbal force that has to react S1 and S2, can be calculated by summing moments about the CG, knowing that there is no, you don't want this to start rotating like a pencil. You want to make sure that things are in balance. Otherwise, if they start to rotate as a pencil, that could be a problem. So you can sum moments about this point, and the gimbal force times this distance h. So gimbal force times the distance h has to be equilibrated by the force, lateral force here is 1 times xp1 plus x2 times xp2. And so that will give you the moment that balances F gimbal times H. I invite you to check that later on, and you will see that's the right answer. F1 and F2 and the weight and the thrust go through axis vehicles, so they go through a CG, and they don't contribute to the moment. But if the thrust was slightly offset, then it could contribute to the moment. So now I have the gimbal force that goes here. I have S2, S1, and I'm getting closer to understanding how I need to proceed forward. The total lateral force experienced by the rocket then is then S1, this S1 here, S2, and the F gimbal force here. All of them are traveling to the right, you can see that. But clearly the vehicle is not going bananas and starting to move laterally in space. It's getting balanced by the inertial forces in the lateral direction. So the total lateral force experienced by the rocket then is S1 plus S2 plus F gimbal, which is S1 plus S2 plus that. The total weight of the vehicle is W equals W1 plus W2 and so forth. So I have the total force of the vehicle, I have the total weight, and so I can calculate the lateral load factor NX that balances the summation of forces. Remember, summation of forces equals MA. And so if I take the summation of forces equal MA, I can then calculate the lateral load factor because of these forces. Because the system has to be in equilibrium, it has to be balanced by inertial forces. So the lateral load factor then, NX, is NX equals S1 plus S2 F gimbal. So that total force divided by weight. And so that's what you get. S1 plus S2 plus all that divided by weight. And notice how this is also equal. Um, yeah, so this is the lateral load factor because of inertial effects. Um, so if I have summation of forces equals AMA, for example, and I divide both sides of the equations by the weight, on the left hand side you get this exact same equation. On the right hand side I get acceleration, right, divided by G. And so that's telling me how much acceleration I have G. So how many accelerations I have above G. That's what this lateral load factor is. And so and the axial load factor can also be calculated. So summation of forces equals MA in the axis of the vehicle. So that's thrust, and then it's balanced by weight, F1 and F2. So if I take thrust minus F1, F2, and I divide that by weight, again now I get now the axial load factor as well. So now that I have that information, I know for a fact that there's inertial loads acting at the centroids of each of these components. And I know that the values are nx, so I know the nx calculation. I can take nx times w1. That tells me how much inertial force I have at the centroid. Nx also here, nx times w3 for this component in the centroid, which is about there somewhere. Nx w4, which the centroid of this cylinder is about here, and then nx at this cylinder nozzle, which is about here. So a little bit shifted to downwards, but you get the idea. So now that you have this, you know everything here. You know S1, you know the weight of the components, you calculate the NX, so you have all that. So now all you have to do is a free body diagram. You can do cuts to figure out what the shear diagram looks like for this, if you treat this as a beam, for example. And so the sum of forces in x direction should demonstrate that the system is in equilibrium. You can check it later. But if I sum forces in the x direction, you get S1 plus S2 plus F gimbal minus nx times the weight, and that will be equal to 0. You can check that later. Shear diagram can be readily plotted now, and then you can calculate the moment based on the shear diagram. I will do some examples later to remind you how that's done. Note that the shear moment at the very top of the rocket is 0. Like at this point, there's nothing going on. And so therefore, at the very bottom, you should get 0 shear as well, which is very weird and different from what you may have seen in mechanics of materials. So very, very important consideration. So from there, you can construct the bending moment diagram if you have the shear diagram. You can also sum forces in the z direction, including the inertial effects that have to sum up to 0. And you can check that. An axial internal force diagram can now be constructed based on this information, and it can be noted that the actual forces increase significantly towards the base of the vehicle. You can see that if I do a cut here, you have the weight of all this times n, z, and then you have F1 and F2 pressing against that. That's what we saw earlier on, that this is the axial load in compression. You can see how it's increasing as I go downwards along the vehicle. So it does make sense that that's what's going on there. If I do a cut across AA, then the force across that free body diagram, which includes just this rectangle here and the triangle, the conical and the cylinder here. So if I cut right here, you get F1 plus NZW1. So that's a force acting in that cross section. If I do a cut here, then I have all these forces in F1 and F2 added together to give you the force balancing across this cross section. And then if I do a cut here, then you get everything above it. So that's how you construct the free body diagram. And note that if I do a cut somewhere where you have pressurization, you have to be careful and you have to consider those effects when you calculate the effective force at that cross section. So here's an example. So if I were to have a tank here somewhere, and the tank were to be pressurized during flight condition, in this example there's no pressurization, say, but in this example there is, and this is more normal to have that situation. Um, and so if you have a pressurization aspects, and now cut the DD here, like a cut DD, um, and I assume the pressure in the tank is P inside, the diameter of the tank is 2R, we will then determine the axial load right here at this cut. Not only have these loads acting downwards, now I have this pressure acting on the surfaces that need to be considered. So to do that, we can consider it. So assume that the whole thing has uniform pressure, which is not true, but just assume for a second. So then the cut at ADD is basically NZ times W1 plus W4 all the way to W4 plus F1 plus F2 minus pi P times pi r squared, which is pi r squared is a projected area of this dome. Notice how that pressure inside is reacting against this dome. And so that's why you get a force that has to get reacted this way. So pressure times pi r squared plus ADD. Now I can solve for ADD, and I can then find the force at that cross section because of that. Um, Equivalently, this is equal to thrust also plus NCW5, and so I can substitute that by this and calculate ADD as well. Note that the axial load diagram can be constructed for based on this information. So I hope that's clear. Uh, and please pause. Sorry about that. And so I can construct the actual load diagram based on this information from tip to the very end. You have to do several cuts everywhere you can find and then do the actual load diagram, which is going to play a big role when you try to do structural qualification. Because, for example, I can do a cut here, and at that cut, I'll get an axial load, a shear load, and a bending moment. And all those three need to be used later for designing. Now, I do want to make sure you understand that in a tank, in a stage tank, for example, you're gonna have liquid. So the reality is that you're not gonna have a uniform pressure. You're gonna have some level of fluid at the top, and the empty space is called ullage pressure. You're gonna have some amount of pressure there. When you go deeper into the liquid, the pressure increases, and we know from this equation for pressure that pressure equals rho times z, the height of the fluid from the free surface. So as z equals 0, you get the ullage pressure. So you say that the fluid level is about here. At z equals 0, you get the ullage pressure at the free surface. Uh, when you go deeper, that pressure increases. Now I have added here gravity plus acceleration, because normally you don't see A, you just see rho z times g plus ullage pressure. But in this case, now we have the action of gravity making things worse. So you do have to account for that. So axial force at a distance z from the free surface due to pressure effects then has to be considered. So now not only have the minus p pi r squared, which is this term, now you have to add the additional effects from going deeper from the free surface down. And so if I do a cut down here, now I have this z here, this distance, and now I have to account for this acceleration here, a. So that needs to be considered, and it is important. Rho is the density of the fluid, which could be uh, LOX or RP1 or one of those fluids, uh, either for the oxidizer tank or the fuel tank. So that needs to be considered in your analysis when you look at this. So once you have the free body diagram across the whole thing, so doing section cuts, and you get the axial load diagram, the shear diagram, and the moment diagram. Once you have all that information, you can look at every component now. And say you have a shear load, an axial load, and bending moment. You may have torsion as well. I didn't cover that here right now, but you could have some amount of torsion. Um, and based on this information, you can come up. It is convenient to come up with an equivalent load that's axial and equivalent shear load. Why is that? So let's look at this. So when I apply an axial load in compression, say, the vehicle will be mostly in compression, and I apply bending, this side will be in compression and it's going to be additive. So you're going to have the axial load plus the bending load, which is going to cause compression on this side. Well, on this side, you're going to have axial load and then the bending is causing tension here. So the worst case scenario is that everything is in compression. So therefore, you can come up with an equivalent load that replicates the worst case azimuth. In this case, will be here because you have axial and bending coming together and adding to each other. So that will give you a P equivalent. That's assuming now that every point around the azimuth has the same equivalent load. That's not the case in real life, but it is one way to make everything simpler when it comes to testing or whatever you're trying to do. So in structure analysis of launch vehicles, applying a uniform load that bounds all the loading conditions simplifies your structural assessment. You can also do the same thing with shear. So you have the shear load and torsion. You can come up with an equivalent V equivalent or shear equivalent load. I want to give an example of a square cross section so you can get an idea how to do that. So this is a square cross section. I have a bending load and an axial load in tension, could be in compression. The stress is P over A plus MC over I. P over A is the axial load. MC over I is the bending load, the stress due to bending. And C is obviously is going to be the, yeah, so this is, I should have said that this should be Y. So you may have seen in books is C, but that C is not this C. So I changed it to P over A plus my over I. And I want to come up with an equivalent load P divided by the cross-sectional area that's equivalent to all this effect. And to do that, then I can multiply both sides of the equation by A. So this A cancels out and I get MAY divided by I. So I have P plus M times the cross-sectional area C squared, Y C over 2 because one side of the square is C. And then the inertia is 1 over 12 BH cubed, which is C times C cubed for cross section, that's square. And so now all this C cancels out and I get P plus 6M over C. You can see here that if I know the moment and I know the axial load, I can come up with an equivalent load P that gives me the same effect as having to look at moment and axial load separately. You can demonstrate that for a circular cross section for a thin wall with mean radius r, P equivalent equals P plus 2M over R. There will be something in a homework or I invite you to pause a video in YouTube and kind of see if you can get this, but this is what you will get. For the torque applied, if you have a torque applied and a shear load applied, then the V equivalent shear force is shear plus torque divided by 2R. So knowing the moment diagram, axial load and shear load, we can determine the axial load distribution along the length of the vehicle, and the shear and torque distribution can also be computed. The information can now be used to inform preliminary design, which could inform structural testing, But you definitely want to do a couple of those analyses and do a more advanced analysis to make sure you're not missing anything. The Saturn vehicle was designed like similarly to this, but they had to do some couple of those analyses. Let's look at terrestrial winds for a second. That's another loading condition. This is considering flight, right? But there's another condition called terrestrial wind. On the right hand side, you see a vehicle that's attached to the ground with, say, hold down pins, which are quite common. And normally 4 pins, but you can have more or less. And here I'm showing a vehicle which has sections A, B, C, D, and E. And the purpose of this problem is to look at what are the loads, the base bending moment, because that can cause a failure here at the bottom. As you can see, if the wind is pushing against this, basically a flag if you think about it, but it's a rocket, then it's going to cause a huge bending moment in the base. So the idea is to determine the hold down pins, the base bending moment at the base of the vehicle due to the ground winds, which can be significant. Normally, what you will use is a NASA Handbook 1001, and that handbook provides basic peak wind speed profile information for test, freestanding, launch, and liftoff conditions to ensure that you have a good performance of this aerospace vehicle when it lifts off. To establish this vehicle responses, the peak design surface winds are assumed to act normal. So if I have winds coming in, I'm going to assume that that wind is acting against the projected area of the cylinder and and is acting in the most critical direction. So the design wind profiles for the NASA Kennedy Space Center can be used. The peak wind profiles are characterized by two parameters, the peak wind speed at 18.3 meter level and the shape parameter K in the equation here. And that describes a wind speed distribution as a function of elevation. So at that reference height Z of 18.3, this becomes 1, and then you can find the speed at that location. And then you have K, which is a parameter that tells you the wind distribution as a function of where you are. And you can see it's going to be, if it was K of 2, then it's kind of like parabolic, say, with the highest distribution at the top. Obviously, when Z is 0, you're here at the bottom in the boundary layer. Basically, you have no speed at the bottom, but it's going to increase uh, in this manner exponentially. Once you define this velocity at this level in K, the peak wind speed profile will envelope um, the problem completely. It will completely specify the problem. Accordingly, you want to construct the peak wind profile for KSC in the context of the launch vehicle loading and response calculations. And you do need two pieces of information that are quite important. First, you want to know the risk of exceeding the design wind peak speed at that reference level for a period of time. So the longer you're in the launch pad, the more likely you are to exceed the design wind peak speed at that reference level. Once this quantity is given, the design peak wind speed at that reference level is known, and I'll show you the figure for that. So here is the peak wind speed, and here's the probability of wind speed not being exceeded. So if it's 365 days, obviously the peak speed winds will be higher. So if I'm at 99%, I don't want to exceed 99% of not exceeding that uh, peak wind speed, then 365 days, that means you have to design for maybe 70 knots. But if you roll to the pad and you're 30 days on the pad, maybe the value is lower. And so you have to really look at the peak wind speed for the windiest reference period versus the probability of for severe exposure periods applicable to this design. I want you to note that this is based on statistical data and is been measured over time, and you can find that information. So, secondly, the risk associated with compromising the structural integrity of the vehicle once the reference level design wind occurs must be specified. So, the second quantity and the reference level's peak wind speed will determine the value of K that is to be used in the equation here. So I made up one here called a vehicle called Polar Bear One. I just made it up. The designers would like to ensure that the peak wind speeds will not exceed 99% probability and when the vehicle is 1 hour on the path. So I'll go here 99% and look 1 hour on the path, and that'll give me a value. For K, we can use, for example, here I have various levels here. So here is the speed. So I look at the speed value. So I find the speed from here, u, and I come here into this formula, and I look at this graph. And the value of k can be determined depending upon where you're looking at in terms of um, um, statistics. So you can see here this minus 1 sigma, 2 sigma, 3 sigma, plus 1 sigma, plus 2 sigma, plus 3 sigma. And you come here and select the value of k based on that. So if I want to use a plus 3 sigma value from that figure, you can then fully calculate u. And notice that this speed by itself is not enough. What causes the vehicle to bend is the pressure of that wind pouncing on that vehicle. So you definitely want to use a pressure calculation for that. And that's going to be zero point 0.5 times CD, the drag coefficient, times this velocity squared times the density, the air density. The drag coefficient is typically zero point 0.8. You can just use that for now, but it could depend on wind tunnel testing. The diameter is known, so you should be able to take that pressure and translate it into a projected area. That's going to cause the vehicle to bend, and you should be able to do section cuts to determine the shear and then bending moment distribution. And then that will give you you can then sum moments about the base and figure out what needs to be done for that. So that's the example for terrestrial winds, how you approach it. That base bending moment that you find and across the vehicle needs to be evaluated to ensure that you're not going to break the vehicle, that the vehicle is robust enough to survive the loading environments. So yeah, so that's how you go about that. Sloshing can be a significant concern. NASA SP 8009 provides quite a bit of information that I advise that you go through. Sloshing of propellants may adversely affect the stability of a space vehicle and the integrity of the tank structure. Sloshing describes the free surface oscillations of a fluid in a partially filled tank. So, for example, if I have some amount of fluid level and the vehicle is vibrating, that fluid is going to start sloshing around, and that's going to increase potentially the pressure on the tank and cause some oscillations as well. And it could introduce angular motions of the vehicle. Such displacements or motions can be caused by a lot of factors. You can get wind gusts during powered flight, program changes in vehicle attitude, attitude stabilization, control pulses, separation impulses, elastic deformation of the vehicle. All that can cause sloshing. And it will depend on the tank's geometry, the propellant properties, the effective damping, height of the propellant, acceleration field, and motion of the tank. So an overview of sloshing. Slosh is basically movement of liquid relative to the container, the tank. Baffles are typically used to separate the tank into sections, and it will keep sloshing limited to that section while allowing the fuel to flow at a very slow control rate. Because if you didn't have those baffles, all the fluid is going to start sloshing and splashing everywhere. Flapper valves are also used in aircraft that use it to limit fuel flow to one direction, and that will prevent backflow during sloshing. Ballast balls can be used. It will float on top of the fuel, and that will increase the surface tension of the fluid, um, and it will prevent splashing and sloshing. That's a good way of keeping everything in check. Deflectors, so a structure deflects incoming waves to absorb the energy and dampen it. And you can also have tank compartments. We'll divide the fuel mass, reduce the effects of sloshing, and increase the natural frequencies. There's also other approaches using diaphragms that help reduce the sloshing. Here, you see flapper check valves that are used, um, and that prevents sloshing in, say, the G450 wing. Here's a fuel hopper. Here's a vent plenum. And then you have the flapper check valves that allow, and these are the flapper check valves here that prevent the backflow that could be detrimental. Here are some of the modes that you can see in slosh modes. The first mode has the longest period of all the normal types. The liquid here sloshes side to side. The second one is more like tidal waves, which have a nodal circle. The waves typically will meet at boundaries at a right angle. So you can see here's a right angle there, right, almost like a right angle. Um, and and that makes sense for the boundary conditions. Here is a slosh mode equation. So for lateral slosh in a rigid cylindrical tank with a flat bottom, the frequency in radians per second of the free surface motion is given by this equation, and that came from NASA SP 8009. And G is the longitudinal acceleration. A is the tank radius. Don't confuse this terminology with what I used in the previous section. And epsilon n is determined from the root of the Bessel function of the first kind. I'll show you that these values are provided. Um, Given that information, you can find omega n. Here, h is the fluid surface height. And so epsilon n can be found depending upon the slush mode of interest. And for liquid height greater than the radius of the tank, the frequency can be approximated this way, makes it easier. And the lateral sloshing of liquid propellants in a tank results in a pressure distribution on the walls. The distributed pressure loading is important for detailed structural design. So here is an example. So here's the pressure. Earlier I showed a pressure equation that looks like this. I apologize. It looks simply like this. That's your pressure equation. But when you have sloshing, you have to add more information. And so here it is. So you have to apply, uh, you have P naught, which is the ullage pressure, then rho GZ, which is a distance from the fluid to any arbitrary depth. Then you have rho G eta, which is the maximum wave height above the fluid surface. And that's multiplied by the Koch ratio function. And here you have the height of the fluid surface, and Z is the depth at which you're evaluating. And then A is the radius that you have. We're talking about omega 1 here is a fundamental slosh frequency. So we're looking at this here, the first slosh mode 1.841 substituted here. And so that's why you see the equation being given here. So that comes into play. And that tells you how the pressure is oscillating as a function of time. And that can be a great input into your analysis to study the lateral sloshing at the lowest natural frequency. And that will give you the pressure amplification, because before I did not consider this term, but I'm showing that this term can exist because you have the sloshing going on. You can also have sloshing in the longitudinal mode. And in this case, the pressures are integrated over the tank bottom and walls, and the estimated fluid pressure forces then during sloshing in the first longitudinal mode in the circular cylindrical tank is given by this formula. It's a little more complex, but you can calculate. It's not that bad. Again, similar formula, rho g z again, and then you have this eta coming into play. Um, Here, remember, g is a longitudinal acceleration field, so it's similar to the to what I had here uh, that I had considered. A plus g. That's your acceleration field. Sorry about that. And so let me remind you how to do free body diagrams really quickly. Say I have this beam that's pinned a rotor with a distributed force, length L half, L half. What I want to do is find these reaction forces here and here. In the rocket, this is a free condition and this is a free condition, but you may have like the condition of the ground winds before liftoff, where it's fixed at one end. You will have to find the reaction forces there before you start to cut across. So I'm going to do a cut here at D and E, for example. I'll cut at D and E. And you can see here I have the reaction forces. Since I have a pin condition here, I replace that with YA and XA. And then here I have a rotor support, so that's YB. And so now I can do cuts and figure. We have to figure out how to proceed now. And so some forces in the x direction, so XA0 from there, YA plus YB, YA plus YB is W naught L divided by 2. And you can sum moments about point A to get rid of these two reactions, which will then give you the reaction forces. Once you have the reaction forces, now you can do a cut at an arbitrary point D, and that gives a shear force and a bending moment at that plane. This distance is x. The reaction force is 3/8 W naught times L. That's what this is. And I'm going a little bit faster because you should be very crisp about mechanics of materials. If you don't, watch one of my YouTube videos where I go into more detail. So I can now proceed now. This W naught times X, that'll give you the total force here. And I can calculate the shear distribution for this section. And you can see here is W naught 3/8 over times L minus X. That'll give you the shear at any point in this section. And then from here, I can calculate the moment, which you can actually calculate by integrating V. That's one approach. But you can also sum moments about a particular point here, and that's easy to do. And I've shown it here. You have M1, which is this one, plus W naught X times this distance, and that distance is X over 2, minus 3/8 W naught times L times this distance X. That balances these two, this shear load that causes the moment. That's this term here. So I can solve for M1 and I get M1. And I can plot it now. Sorry, now I have to look at this section here, this section E. I have to do a cut there. When I do a cut there, I apologize. I'll do a cut here. And I'll look at the right-hand side. The right-hand side, I have the reaction force 1/8 W naught L. Very similar process. Do a cut, calculate the shear and the moment. And sum of forces in the y direction is V2 plus 1/8 W naught times L equals 0. And then you also can then solve for V2. And then the moment can also be calculated by considering this force here, which is 1/8 W naught L times L minus X. That gives you the moment. You can then plot that out, and this is your shear, and bending moment diagram. Note they can also construct this bending moment diagram by integrating the shear diagram. You can see here there's a straight line, so the derivative of this straight line gives you a constant, or the integral of a constant gives you a straight line. So, and then there's a quadratic shape because this shear is uh, uh, a function of x. And so you can integrate that to get a quadratic shape. Another example problem here, very quickly, I don't want to spend too much time, but you have here the shear loads applied. So I want to do a cut here in AB. And my whole intent of this example is to show you where to do a cut. Cut here, cut here, cut here, and cut here. Very similar, you're going to treat the launch vehicle. Now here, this reaction force has to be replaced by a force A, and then here it needs to be replaced by another force D, a point D. So again, you can do cuts very quickly. You can find through summation moments about A and summation forces in the y direction that the reaction force D is 26 kips here. So that's 26 kips. This reaction force is 18 kips. And so now I can construct the shear diagram by doing cuts successively at the different locations I told you about. And so I will get 18 going up, and then it drops 20. You can see that there. So I have minus 2. It drops another 12, so I get minus 14. And then it goes up by 26, so it goes to 12. And then I have a linear distribution of load. That means it drops linearly down to 0. And that can be easily calculated. So once I have the shear diagram, you can also integrate that. Um, and if you integrate this constant value, you get this moment, which is linear now. And so again, you have to do each of these, integrate the moment. So dm dx equals v. So integrate this equation. Um, I apologize. Just want to show how it's done. So by integrating the shear, you can construct the moment diagram fairly easily. Look at this area under the curve, that's 108, so that represents this slope. And then if you look at the area under this curve is minus 16, so 108 minus 16 is 92. So that tells you exactly where I have to stop. So 108 drops to 92. And then I look at the area under this curve is minus 140, so this point has to go from 92 down to minus 48. And we know that this has to be quadratic here in nature. So that can be just integrate the shear formula for this section to get that bending moment. Yet another example here. Here I'll do a cut here, and then I can calculate the shear and moment diagram. I don't want to spend too much time to do it because you should have done this in mechanics and materials. But here, what you want to do is find the reaction forces here, and then do a cut here, and then plot the shear diagram. Once you have the shear diagram, you can integrate the shear diagram to get the moment diagram. A quick example of a sizing example for Isogrid. I don't want to go into extensive detail, but if you download this paper, this Isogrid Design Handbook, NASA CR 124075, it will give you a great understanding on how to size a tank, for example. Here's a great paper that shows the design of an interstage structure in a launch vehicle, Isogrid construction. I invite you to download that paper because it shows some great hand calculations. For example, given the geometry, the rib depth, the rib width, the skin thickness of that Isogrid, triangle height, and leg of the triangle, given this information, you can then, based on the axial compression, the P equivalent we talked about, we can then determine whether we have a general instability issue, a skin buckling issue, or rib crippling issue. So here I'm giving you the formulas based on the Isogrid handbook, but it will be very easy to go through the steps there and calculate whether we have an issue in the design. Notice that the loads are considered in this paper are the same ones we've been talking about: axial, bending moment, and shear. And notice how the equivalent axial load was calculated exactly how we discussed it earlier. So it does show the process really, really well. Um, Generally speaking, we are, um, I think we're doing the right thing going through these calculations. They also then do a finite model to increase confidence in the calculations, and they include cutouts because obviously um, we want to make sure that the structure can survive the cutouts as well. So finite element analysis was done right after to improve the design further. I want to now talk about sizing an example for a solid rocket booster. Very, very top level, nothing very big, but in a solid rocket motor, you're going to have pressure inside. So the circumferential stress is PR over T, and the longitudinal stress will be PR over 2T. You're also going to have to look at the strains in the propellant. So if this is a metal or composites, the inner here, right here inside, and the source here is NASA SP 1073. This is a grain here. And so this analysis considers both the effects of temperature change, because temperature can cause stresses in this grain. And actually, when you store a launch vehicle, like a rocket, a solid rocket motor, you want to store it potentially at a temperature that's adequate for protecting the solid rocket motor. Now, the cure temperature of propellants can range anywhere between 100 to 200 degrees F. And so when you cool it at room temperature, even that's going to cause some amount of uh, the grain is going to pull away from the uh, wall, which is going to cause stresses in the radial and circumferential directions. And the formulas are given here. You can see alpha is the coefficient of thermal expansion of the case. Alpha here is the coefficient of thermal expansion of the propellant, and E is the modulus of the propellant. So all the information is given here very quickly. Omega is given to you as well. And A is a bore diameter, B is a radius to the inner portion of that case. So all that information is given very well. So these are straightforward calculations. And the important thing to remember is we don't want to have a failure due to stresses being too high during storage. Some of these rockets can be stored over 10 years, says an example. You can also calculate strains. Strains can be very useful because a lot of the propellant data can be given in terms of strain as well. So it can be very, very advantageous. Now we can continue here. So we have uh, internal pressurization. So storage is going to cause stresses, but also pressurization. So when you apply pressure inside the bore, it's going to cause stresses in the grain as well. And so the formulas are quite straightforward, are provided here: radial and tangential stresses, and the strains can also be calculated fairly straightforward. The difference is when you have internal pressurization that occurs at a high rate, because that's how pressure gets applied to the grain, and as a consequence, the modulus will be slightly higher than during storage because the propellant behaves viscoelastic. So those properties can be found through testing. You apply a tension test, and that test determines if you apply it slowly, it gives you long storage conditions. If you apply it quickly, the modulus will provide you, the test will provide you modulus at higher rates, which is important for grain design. You could also have the situation where you have a launch vehicle that's obviously when it takes off is horizontal. So when the vehicle takes off, it's going to impart acceleration downwards, and that's going to cause a shear stress in this grain, and that shear strain is given by rho n r, and n is the number of g accelerations. And I showed you how to calculate n from the launch vehicle design problem earlier. Typically 4Gs, 3Gs, about that. So you don't have to even do that calculation. R is a radius location, and A over R, A is a radius out here. R is the location where you're at, and at R equals A, which is right at this boundary, you get zero shear stress, because this becomes 1 is 0, and that matches what happens at the boundary. The strain and displacements can be found simply as this. And again, this is an important calculation because when the vehicle is taking off, you don't want this grain to fly apart. There's a stress Rourke's formula handbook, which has a chapter 13. It has a great number or formulas that can be used to calculate the stresses due to various conditions. And it has cones, has truncated cones, and domes and things like that. So that can be very, very advantageous for the sizing of launch vehicles. And so you'll be seeing some of that in some of the work you'll be doing. Well, you have a great rest of your day, and I hope that you stay safe, and I'll see you in the very next lecture, which will continue discussing launch vehicle design.